Hello. So we continue our discussion of the derivation of real fluid equations, okay, starting from a distribution function which has a small perturbation, first order perturbation with respect to the zeroth order local Maxwellian distribution. So we just stated last time that BGK equation considerably simplifies the total formalism just by saying that only one of the term, that is the last term, okay, of the last term of the four terms of this expression is sufficient to adequately recover all the transport phenomena in a usual fluid. Okay. Now this was done by three scientists, Lippmann, Narasimha and Shahin. Okay. So we said that finally a very reasonable approximation gives G is almost equal to minus tau del f0 del t plus u dot nabla f0 plus a dot divergence of u f0. Okay. So f0 we know. What is f0? f0 is nothing but the local Maxwellian distribution. So now we have to calculate these three terms, a dot nabla u f0. Now we know that f0 is the local Maxwellian distribution, so calculating this part is reasonably direct, because in f0, if you see the f0, so this is the form of f0, the dependence on u is only here, and this is explicit dependence. Okay, and that's why this is direct to calculate. So please calculate at home. Once again, in this course it will be not possible to do all the steps of intermediate algebra, but you are supposed to check all the steps of algebra at home. If you, in case you are blocked, you can ask me, or you can just refer to one of the books which I suggested in your course handout. Okay. Then we have to calculate also del f del 0, del f0 del t, del f0 del xi for this term, of course, this one, okay, and this one corresponds to this one. Now for that we have to realize that fact that in f0, which is a local Maxwellian, the space and time dependence, explicit space and time dependent, they come through three variables, in, t and v. Just look here, in, t and v. Okay, so when we will try to calculate del f0 del t, the total expression will be simply this. Okay, that is del f0 del n del t plus del f0 del t del small t plus del v del t dot del f0 del v vector. So once again, this is a fancy way of writing the gradient of v, gradient of v of f0. Okay, this. So in a similar way, you can also write del f0 del t, okay, as a summation of all these three terms, okay, through their implicit dependence of n, t and v. Now once again we can remember, we can recapitulate the functional form of f0, which is a local Maxwellian. Okay, so now you have to do step by step some straightforward but careful algebra. If you make some mistake over here, then you will be lost. So do slowly, even at home when you will practice, do slowly but step by step. Do not do any step jump. Okay, and this will finally give you G to be equal to the whole thing. So it may look like a bit, I mean, lengthy or a bulky, okay, but believe me, if you try to understand segment wise, this is quite interesting. So one thing you can see that G is minus tau, so this is minus tau is over there and minus tau is over here, okay. So inside the bracket there are several things. So there are f0. So now del f0 del t u dot nabla f0 a dot nabla u f0, all these things gives us finally a factor times f0. Okay, so finally again this whole thing is, I mean, proportional to f0 as well. Okay, this is also proportional to tau. Okay, that is very interesting, that it directly says that when your system is strongly collisional, tau is very small, your G is small. When tau is big and your system's collisionality is very weak, then you have basically a considerable G. Okay, so finally the total so G is consisting of globally two type of contributions. One comes from this, and this one is proportional to del t del x I. Okay, another one proportional to lambda ij. If you remember what lambda ij was, so lambda ij was just the velocity gradient tensor. It was like this, del vj del xi plus del, maybe I just write the other way around, but in any case that is not a problem because this is a symmetric tensor. Okay, so this is what lambda ij is. So one term should be proportional to the temperature gradient. Okay, and you can see this term has an odd dependence on the components of u vector, because there is always one ui which is unpaired, and this is u squared, so this is even, and there is nothing, so this is also even, I mean in terms of components of u. So only one ui is multiplied, which makes component wise the thing odd. Now another part, which is the part depending on the velocity gradient. Okay, this has two parts. One is of course clearly even, the another is conditionally even or odd. Okay, so let's say if you multiplied with this term, with this part, something where both ui and uj can pair, then I mean let's say if you just multiply ui and uj with all the thing, then this part will behave as a pair, I mean even combination. On the other hand, if let's say if you just multiply with a single ui, then ui will pair, but uj will be remaining unpaired, okay, or uncoupled. So that will give you an odd contribution. Okay, so this is a conditional part. This part is even always because it's u square. Okay. So previously, now of course this is the G which we can get. Okay, so you see, after all these simplifications, finally we have a form of G which looks like a bit frightening, but believe me, finally this is a very handy form. So you can decouple the total contribution as a sum of a contribution which is proportional to the linear temperature gradient, and that is a linear velocity gradient. Okay. So if you remember now that from your basic knowledge or previous knowledge of fluid dynamics or something, so it is somehow expected that the heat transfer should be related to this term, and momentum transfer or the viscosity, basically you know that, right, that viscosity is nothing but a transfer of momentum or transport of momentum, okay, should be related to that. And one of the very simplest models we know is the Newton fluid model, Newtonian fluid, that I will come later. Okay, but roughly speaking, you can easily understand that maybe this part is related to the thermal conductivity part, and thermal conduction or thermal transport part, and this part is related to the momentum transport part. And we will see that there is no exception to that. What we have guessed is actually correct. Okay. So previously with Maxwellian distribution, we had simply Q is equal to 0 and the pressure tensor was trivially diagonal with a single value of the that says that all the diagonal elements were equal, so it was simply a scalar. Okay, so we will now calculate again Q vector and P tensor with this new distribution function, and as we can expect that Q will no longer be 0, Pij will no longer be purely diagonal, right? So for Q we will have by definition this term. The F is now written as F0 plus G, and we know that F0 is the local Maxwellian, so m by 2 integration F0 times u square u d cube u is 0. So finally the term which remains is this. Okay, so non-zero Q basically is an outcome of non-zero G. Okay, so a careful observation now here clearly indicates, okay, that the part of G which is proportional to del T del Xi will contribute to the non-vanishing expression of Q. Why is that? That is something very interesting and we have to learn how to check that. So here you can see component wise, if you think this, there is an odd component, odd functionality of this part, because if you just write it in component you will have u square ux plus u square uy plus u square uz, and from this one if you just do the multiplication then sum of the component will pair with this component, okay, may or may not pair, but finally the other component will be remain uncoupled. So if in case some of them will pair with this uy over here, then one will be remain uncoupled. If none of them pair with that, then simply both of them will be uncoupled. So in any case this will vanish. Okay, same thing for this. This is an even, so even times odd gives you something odd with respect to the component, each component of the velocity. Now here you have an odd contribution component wise for the velocity. Once again, when I say capital U, just remember capital U is nothing but the fluctuation velocity, which sometimes we call c, small c. Okay, so just for recapitulation, capital U is nothing but u, small u minus small v, okay, which is equivalent to c as well. Okay, now only when uy and u, for example uy and uy over here, they matches, they will give something uy square and finally making the global contribution even. Okay, and that's why you can easily see that the only possibility that the Q has a non-zero contribution may only come from this thing. Okay, so roughly speaking that odd multiplied with odd gives even. Okay, now again here you have some a few steps of cumbersome algebra, I agree, but systematic algebra, of course, you have to be a bit careful, and that will finally give you that if you do that algebra. So for this type of thing, it is, rather than doing this algebra, it is rather interesting to understand the physics. Okay, so some steps of algebra can give you that Q is actually equal to minus K times gradient of T. So we already showed that this thing will be, so the part of G which is proportional to this will contribute only. Okay, so Q should be expected to be proportional to gradient of temperature. And if you do that, if you say that, okay, I now suppose that Q is equal to some constant, of course I am writing minus for the conventional purpose, but minus K times gradient of temperature, then one can simply calculate just by comparing this one and this one, okay, and by replacing G by this part of G, okay. I mean, of course, there should be F0. Don't forget the F0, okay. So if you see that K will simply be tau m by 6t integration d cube u times u to the 4 times m by 2 kbt times u square minus 5 by 2 bracket times F0. Okay. So you see that finally, again, so this integration is all over all the components of the u. So it's a vector, it's integrated over the vector u. So if you do again the integration from infinity, minus infinity to plus infinity, that is the, I mean, domain for of integration for classical cases, you can show that K is nothing but 5 by 2 tau in kb square t by m. So it is important to do the integrations and to actually at least to come from this one to this one. Okay, so if you can do that, finally try to understand what this is. So this is some quantity which is the proportionality constant of Q. It may or may not be constant, to be very honest, but at least if you just see the expression, so it should not depend on U, I mean capital U. Okay, so and it is now you can see that 5 by 2 tau in kb square t by m. So of course there is t, there is n, so it will be a function of, in general, r and t. Okay, so this is not an absolute constant, but this is not a function of kinetic velocity. So this is another macroscopic quantity if you want. This K, when you match your previous results of real fluids, you can see that this is nothing but the thermal conductivity. Okay. Now the physics comes here. You have to note that K is proportional to tau, K is proportional to n, K is proportional to t. Of course, when I am saying proportional to tau, that means n and t are kept constant. So by the rule of joint variation, you can say that K is proportional to tau n t, the product, when all of them vary, right? And individually saying that K actually increases. Let's say I am just saying that n is constant, t is constant. Then K increases with tau. So if in a system, for example, if in a system we just don't change the temperature, we don't change the density, but we just simply say that the collisionality is now become weaker and weaker, then strangely the thermal conductivity increases. Okay, so that the system is a fluid. So that is the problem. So you may have that in mind, that what is I mean the problem here, because n is constant, t is constant, I understand, but then when tau is larger, that simply says that the mean collision time is larger. How can that correspond to a greater K? That is simply because in order that the system still behaves like a fluid, it should have a greater transportability. Okay, so everyone, so K, for example, then we will see, so so this is the story of the thermal transport. So K is the responsible for the thermal transport. So at least the duty of K is to do the thermal transport efficiently. When tau increases, that means the collision basically decreases, right? So mean collision time, okay, increases. Okay, so if this is the case, then you can see that how to say that the system's conductivity should be strong enough so that the system can efficiently transport energy from one part to the other. Otherwise, the system is no longer fluid. But here we have supposed that already we are representing this as a macroscopic thing. So being a macroscopic entity where the collective effects are important, the necessity that tau is higher is that K must be higher. The same thing, if your N is higher, then K is also higher. If your temperature is higher, okay, then temperature is higher means temperature gradient can also be expected to be higher, and then the energy transport should be efficient as well. Okay, so K should be higher. Okay, so these things are inconsistency with each other. Okay, now the question is, that was the story of the heat flux tensor. Now what is the destiny of the pressure tensor? What happens to it? Of course, P tensor will now have a diagonal part, P delta ij due to F0 plus something, plus an off diagonal part, small pi ij due to the perturbation G. Okay, so obviously we now can write that pi ij, that is just due to G, can be written like this: m integration d cube u uy uj times G. That is the definition. Okay. Now again, careful observation. That simply says that here you see that here you have uy uj. So if you just take this part, the part which is proportional to del t del xi, you will see that uy may couple at best with some of this ui, with one of the ui and uj, right? But one will always be left uncoupled, thereby making the whole thing odd component wise and making this zero to be zero. Okay, so there is no chance of having a contribution from this part. Okay, so roughly again speaking, that odd multiplies with conditional even makes the whole thing even. Whole thing globally odd. Contribution now may come from this part, lambda ij. Now, of course, in lambda ij part, when this is even, so this part can contribute when you have this I is equal to j, and this part can also contribute when I not equal to j, but ij is exactly equal to this ij, so that ij uy uj is now paired with uy uj, gives you uy square uj square. Okay, so even multiplied with even, conditionally even multiplied with conditionally even makes it globally even. Okay, so if you finally write the expression explicitly, you will see this is nothing but pi ij is equal to minus tau m square by kbt times lambda kl within integration d cube u uy uj within bracket uk ul minus 1/3 delta kl u square times f0. Okay, so that is the most general way you have to write. So of course here you see this I and j, they are the free index over there, and kl, all of them are dummy indices. That means there is a sum over this indices. Okay, so just how it works, you just try just by putting this one as 1 2, or this one as 1, this one as 1, for example, and then when you have fixed 1 and 2, for example, then you make a sum over kl, because there is a sum over this. Okay, so that is the part you have to understand. Okay, so because repetitive indices, when they are indices when they are dummy indices, they are basically designating sums. Okay, and this part Again, careful observation. This part simply says that the above form of pi ij represents a traceless tensor. Why? Why is that? What is the meaning of traceless tensor? That means if you sum, if you say that I take pi ii, that means summation over pi ii. Basically, there's a conventional meaning, that is pi 1 1 plus pi 1 2, plus pi 2 2 plus pi 3 3. Okay, the whole thing will be equal to 0. Okay, and how is that possible? Let's say we just make, so we just say that pi 1 1, so when this is 1 and this is 1, so this is also 1 and 1. Okay, and we inside this you have, so every time you have u square minus 1/3 u square. So after when you sum all these three things, okay, you will have finally that a summation, okay, where you will see that finally you will have u square minus u square. Okay, because this term will then contribute thrice to make it a u square. Okay, and here you will see that this term will then be simply u square. Okay, and then finally it will give you something, a traceless tensor. Okay, so this is the necessary condition for a traceless tensor basically. Okay, yeah. Okay, so other than that, I think in this point you have this type of thing totally done. So this is the symmetric part, of course, and this is the symmetric part, I agree. So what else to see? So another interesting thing is that, okay, so another interesting thing is that this thing, let me just, sorry, yeah, this thing. So that was just by, I mean, just from its expression you can see that the trace is 0. Okay, so this is an interesting exercise for you. So try at home. If you are blocked, you ask me. Okay, so again you can notice here that pi ij, okay, when we just defined that pi ij from its basic definition, it is proportional to pi ij. Okay, sorry, lambda ij. Okay, so if it is proportional to lambda ij, that is so that is also our consideration, that this part will now contribute for pi ij, so it should be proportional to lambda ij. So we can simply say that if this is proportional to lambda ij, then of course it is tempting to write that this pi ij is equal to some constant times lambda ij. But we have to remember always that the property of tracelessness should be satisfied. Okay, and for that the correct way of writing mathematically pi ij is not simply this one but this one. Okay, that is pi ij is equal to minus 2 mu, which is a constant, bracket, okay, lambda ij minus 1/3 Kronecker delta ij times divergence of v. Okay, and we subtracted this part because we know that the trace of lambda ij is divergence of v. So again, starting from this expression, this is another small exercise for you to check that summation over pi ii is equal to 0. Okay, now our question is, now we have introduced mu as a proportionality constant. Can we obtain an expression for mu? Okay, for that, of course, we should calculate pi ij when I is not equal to j. Why? Because when pi is equal to I is equal to j, then this part is 0. Okay. I is equal to j, sorry, this part is non-zero, this part is non-zero. Okay, but uh, sorry, yeah. So when I is not equal to j, so then what happens that yeah, mm, then you can easily see that, for example, if I write here over pi 1 2, let's say I just take I is equal to 1 and j is equal to 2, then pi 1 2 is nothing but tau m square times kbt lambda kl integration d cube u1 u2 times uk ul minus 1 by 3 delta kl u square f0. Okay. So just it's a very small brain twister. Can you immediately tell me from the expressions of pi ij why we have to calculate pi ij with I not equal to j to calculate mu? Is it possible to do that? Hmm? Okay, so I mean this is a very easy question to understand. Okay, so you can think and you can ask me, you can tell me. Okay, so I mean just have a look on this expression, this expression. I'm sorry. Yeah, sorry. Yeah, this expression, and along with a bit of this expression. Okay, and you will tell me mostly you need this expression. Okay, that why you need, I mean not this one but the correct one. Yeah, why you need the I is to be not equal to j, okay, for calculating your mu. What is the problem if I is equal to j here? I mean you can see that because I mean you have to also use this information that the trace of I pi ij is divergence of v. Okay, and you tell me. Okay. Okay, now if you take I is equal to 1 and j is equal to 2, for example, then there is no problem and you can write the whole expression as this. Okay, and this expression finally comes out to be tau m square by kbt lambda kl integration d cube u1 square u2 square f0 finally. Okay, because the non-zero contribution only comes from the conditional part of g. Okay, finally we compare this with the expression star, this expression, this one, the star. Okay, and if you do that you will finally see that mu is nothing but this tau m square kbt integration d cube u1 square u2 square f0 is equal to, that is equal to, if you do correctly this integration, finally you will see this is nothing but tau in kbt. Okay, of course you can calculate mu just by taking, let's say, I is equal to 2, j is equal to 3, or I is equal to 2, j is equal to 1, or I is equal to 1, j is equal to 3, anything, but I is not equal to j, and you should find the same result. And to our utter surprise, we can see that just like k, mu is also proportional to tau, mu is also proportional to n and t. So mu increases when t increases, tau increases, or n increases. Why? Now I discussed about these dependencies for k. Now for mu, you have to think. Okay, this mu, from our previous knowledge of fluid equations, one can match, the fluid dynamists can match and call that as coefficient of viscosity, rather dynamic viscosity, coefficient of dynamic viscosity. When this is divided by the rho, by the density, mass density, it is called the coefficient of kinematic viscosity. But in general, this is called roughly coefficient of viscosity. Okay. So one thing is true, that when temperature increases, viscosity, coefficient of viscosity should increase. Now tell me one thing. Yeah, it's true, I know that for gas, when you increase the temperature, mu increases. But what happens for oil? When you heat oil in a frying pan and you increase the temperature of it, you will see the viscosity, the oil is moving around much more easily on the pan. So can you reconcile that? So this is a question of, I mean, not exactly, I mean, related to the codes, but this is a general physics question. Can you, so what happens? So why the viscosity of a gas and the viscosity of a liquid have different uh, type of temperature dependencies? Okay, so just think, here we are talking about mostly in the, I mean, when we talk about fluid, it is I mean the gas, because here we are just starting, I mean, we are just trying to I mean, we started from kinetic theory and trying to make a macroscopic theory from that kinetic theory, and kinetic theory is only valid for gas. Okay, classical gas. For classical liquid you cannot make kinetic theory because of the simple fact that in a liquid you have interactions, I mean complicated interactions, long range interactions, other than the instantaneous interactions due to binary elastic collisions. Okay, so finally our objective was to search whether we can still build up a dynamical theory for macroscopic variables for real fluids or not. Now for that, let us calculate the following terms of first order moment equation, the del p ji del xi. So for diagonal p we had only this term for local Maxwellian. Now we have the additional term like this, where mu is assumed to be constant in space, and which is very reasonable for most of the fluids. Okay, so there is a case which, when we will talk about the physics of accretion disk. Okay, there is a case, and that is the case of accretion disk. Of course, the mu is not constant in space, and that actually adds a separate physical flavor, okay, to the problem. But here most of the cases we have this. So then we can write this the double contraction term of p tensor and the lambda tensor in the energy equation, which was previously just this term. Now we'll have an additional term like this. Okay, so both these terms are due to g. Okay, g means the perturbation over the local Maxwellian. Okay, now experiments show that the viscous term in 2 is usually negligible, and actually most of the cases this is also negligible, but this is much more negligible and this is much more popular actually. Sometimes even in some cases we can take this, but this is mostly neglected. Okay, so finally we get the equations as del rho del t plus divergence of rho v is equal to 0, continuity equation. The momentum equation can now be written as del v del t plus v dot nabla v. Okay, so these v and these v, they are just equal. Okay, don't get confused. Okay, is equal to minus gradient of p by rho plus g. G is the body force, not to be confused with the perturbation distribution function. This is just the gravitational acceleration. Okay, plus this new term. Now this mu by rho, which I was calling the coefficient of kinematic viscosity, is in general denoted by nu. Okay, as a coefficient of kinematic viscosity times the whole thing. And finally the energy equation is becoming rho del epsilon del t plus v dot nabla e epsilon minus divergence of k nabla t. Of course, here we have not yet considered k to be independent of space, and that is actually not a very good approximation, because most of the cases k has very explicit dependence on space, plus p times, sorry, it will be p times, yeah, divergence of v is equal to 0. So this is, I should write like P, sorry, P, yeah, okay. Now we have again 5 equations, and how many unknowns? So rho V, P, mu, G is known, okay, epsilon, K, okay, and T. Now mu is, in the most of the problems, mu is given for a specific fluid, so it is a constant, of course, other than this accretion disk problem, but even in accretion disk it is handleable. Okay, we will talk about that. K is either a constant or is an explicit function of space. So you can always write that K is like, let's say, proportional to R to the Q, for example, I mean R to the alpha. So then what happens, I mean, if you are just doing some integration, so basically this is a, I mean, explicit space dependence, so this does not add to the complicacy of the unknown variables. Okay, and so K is most of the cases a known explicit function of space or is a constant. Okay, because there are some experiments by which you can actually find the functional form and the functional dependence of K. So it does not really complicate the scenario. And finally, rho, P, epsilon, and T, we know that they are all related by 2 independent variables, and most popularly the 2 variables are N and T. Okay. So finally, 2 independence variable from here and 3 components of V. So 5 equations, 5 unknowns. Okay. So finally we succeeded to constitute a dynamical theory for the real fluids. Okay. So that's exactly where I should stop for this lecture. So in the next discussion, we will talk about a very interesting application of these equations, and we will talk about the hydrostatic condition, okay, the hydrostatic equilibrium of such a fluid, where the viscous effect is negligible, but not the conductivity effect. Okay, so that we will do. And but for this one, in this lecture till now, what we have seen is very interesting, that starting from a very I mean simplistic assumption that the distribution function is perturbed only by a very small amount with respect to the Maxwell-Boltzmann equation. Okay, finally we retrieved all the, okay, under of course certain approximations, all the transport phenomena, okay, in a fluid, in a real fluid. So now this equation, this set of equation is known as the equations of the real fluids. Okay, thank you very much.